不是口水，你要进包吗？放得下吗？啊？你知道放得下吗？可以。All right, this is your distribution of midterm examination. So usually we expect it's a normal distribution, but it isn't. So what is this distribution close to? What is this distribution? It's not bear shaped distribution. What it is distribution. Okay, in probability we don't have linear distribution. So the answer M shape. Okay, it's not M enough. Okay, what else? Can you guess? We just mentioned it's not a normal distribution because we expect a bear shape to be a normal distribution, but it's not a bear shape distribution. Any other guessing? Okay, I think it's um, more closely to uniform distribution because in each region or each position we have very close values for each region. So I will call this uniform distribution. Okay, so what's the reason behind which gives us the uniform distribution? Because for normal distribution, we can expect we have most students in the average range in the middle, and we have few students in extreme both sides. Okay, so for people who have 100 or 0 scores, we have very few students on both sides. But why we have uniform distribution for our meeting examination? What's the reason? Which means we have high values for low score students. And we also have high values of high score students. What does that mean? Okay, so you're trying to explain both extremes, right? If the examination is not hard enough, then we have a very lot of students have high scores. And for this one, they didn't study very hard. Okay, so okay, good. Okay, maybe we can try to think of maybe part of the reason comes from this is the English taught class. So if the student cannot understand well during the English teaching, then maybe that's the reason for in this category. So how about this one? Maybe we have so many smart students this year, and they have good English ability. It's pretty fantastic. Okay, so maybe we have more students in the high school. And particularly, we have one student who has 100 score. Okay. So later on, I would like to invite him or her to stand on the stage to share how he or she gets 100 score. Okay, now I'd like to give your uh, intern feedback. Yu, Han. If I call your name, please come forward to get your midterm. Yu Han, 张玉伟 Okay. Anisha. 郭义山。张凯华。老师有点好，忘了。金的陈俊伦。吴瑞婷。张佩琪。林佳瑜。李维明。郑清燕。叶家健。哈星浩。黄国军。林敬义。林佑任。Justico 黄杰勋。高雨欣。陈佑学。郑有玉。卢国轩。柳信佑。杨炳宏。 赠与谢黄兴吴新纯赖佑汉刘哲凯王威志陈佑二陈世宇魏红嗯 your name is critical to pronounce forward. If you didn't give your return, 廖浩君So how to pronounce your name? Champagne. Sorry? What's your name? Tao. Okay. Hassan Tao. Okay. 张明俊，军佑，杨祥富，黄俊文，杨仁凯，叶国生，陈楚君，周志伦，郭一宇，邓 冠吗？帅。陈千宇。丁向恩。吴明芳。蔡什仲。蔡什么仲？有吗？这个同学。蔡什么仲？吴子。庄心宇。陈元通。黄建军。万里。杨恒安。杨凯任。甘前昌。李维夫。邱国祥。苏胜祥。陈冠奇。林宏志。吴玉佑。刘宇阳。Okay, if you didn't get your midterm, you can come forward to find yours.
Can I take her?
Yeah, sure. Okay, so you can see the average score is 76.5. So if you're above the average, that means you're very safe in this class, and congratulations. So
now I would like to invite the students who have the full score to share how she's done. Okay, let's welcome the student with 100 score. Okay, maybe you can tell me what's your secret to have very good score. Please, please. History, history. That's all. 那你是用中文讲吗？看你们讲完整一点。主要的原因是什么？所以就问到最后。 所以主要就是2点啊。第一点就是有不懂就问 AI，问到会为止。好，第二点呢就是多做考古题。好，那这个希望大家期末能够100分啊。好，那个除了这点之外呢，老师还有另外一个诀窍分享给大家。好，注意看哦。好，如果你的分数是90分以上的同学举手看一下。好，举高一点，举高一点。好，好，手不要放下来哦。好，如果你的分数是80分以上的同学举手看看。好 ，OK， 好，举好哦。好，把手举好哦。大家有发现什么吗？80、90分的人，没有人会坐在后面哦。哦，如果你坐在后面的话，其实你大概都是60分以下。好，所以知道吗？这个叫做地理人杰啊。好，下次上课的时候，后面的同学记得先来站这边的位置哦。这边的位置坐下去就有80、90分了。好，坐在后面，我告诉你差别在哪里啊？好不好？当你坐在后面的时候呢，其实第一个，你看前面的荧幕会看不清楚。好，你如果来坐前面试试看啊，这个荧幕超清楚的。第二个呢，你坐在前面，你会看老师看得很清楚，我会在里面墙晃来晃去，所以你想分心都没办法。好，所以呢，你下次试着坐在前面看看，好，保证会有一个不同的学习体验。好，这个来验一下那个90分以上是什么感觉？这样好，坐在这边的那个学习状态会差异很多，尤其是坐在后面的同学。好，下次试试看。好。
Okay, let's give a very quick review of the answer of the midterm examination to see if you have any question and if we need to explain the question again. Okay, the first question, I think it's very easy. You can check the answer by yourself. The second question comes from our slides. So we just replaced the name of blueberry, strawberry, and cranberry. So that should be fine. And question 3, okay, so
you need to infer by rules of inference and give the name of the rules. So if you're familiar with such as instantial instantiation, generalization, instantiation, so on, then you can replace for all x p of x q of x by some instance such as p of c or q of c. And then I believe you can get the answer easily.
okay, and then use set builder notation to give the description of the set MNOP. Okay, so you can simply write it's a set with English alphabet from M to P, and then you just write in the notation of a set. Okay, then question 5. Any question for question 5? Do we need to explain it A to J? Any question? Okay, so that's all the definition for subset, proper set, or set, or Cartesian product power set. Okay, so if you know the definition very well, then you can distinguish the answer easily. Question 6, 6 also from our course slides. Okay, maybe next one. Okay, show that there's no infinite set A such that the cardinality of A is less than Aleph now. Okay, so for this question, we can prove by contradiction because it asks us to prove there is no infinite set A which cardinality is less than Aleph now. So we assume there is infinite set A its cardinality is less than Aleph now. Okay, so by this assumption, and then we can try to derive the contradiction because if A is an infinite set, then we can choose a countably infinite set from an infinite set by using pick up the first element A1, and then from the original set exclude A1, then we can choose the second element A2. Then we can repeat this process one by one. Then we can choose A1, A2, and 3 to have a countably infinite subset B, which elements are all extracted from A. Okay, so by this fashion, you can see B actually is a subset of A, and the cardinality of B is Aleph now. So we derive the cardinality of Aleph now is less than or equal to A, which is a contradiction to our previous premise. Okay, so that's how we prove there is no infinite set which cardinality is less than Aleph now. All right, next one, give a big O estimate of the function. So we have n log n plus 1 squared plus log n plus 1 times n squared plus 1. Okay, so we can extend all these terms together. For example, n log n plus 1 squared. So we have a plus b squared, a squared plus 2ab plus b squared. So we have first term n squared log n squared plus 2 times n log n plus 1. And then we extend these two terms using n squared log n plus log n plus n squared plus 1. Okay, now we have several terms with the addition. So remember the theory, when we estimate the big O, we just estimate the maximum one when we have multiple terms added together. So let's verify which one has the maximum big O. Okay, the first term n squared times log n squared. So remember, when we have two terms times together, then we need to consider their big O together. So now we have the first term n squared log n squared. Let's compare the second term n log n. Okay, now we can see this is n squared, this is n, and we have log n squared, this is log n. So currently, this big O is larger than the second one. Okay, so how about n squared log n compared to the first one? We have log n squared log n squared. So we have the common term n squared. So we need to compare which one has the largest big O, log n or log n squared. Okay, remember we have different magnitude. If we have n, then we put log in front of n, so we have log n. And we already know log n, the magnitude or the growing is lower than n. That means when you put log in front of some terms, that make it slower. So that means log n is slower than log n. Okay, even it has square or cubic or the or the power is 100, it doesn't work. Okay, it's slower.
Now, this one is the maximum. We can compare to n is like n squared. Okay, so in the end, uh, n squared log n grows the fastest. So this is the answer. The big O estimate of this function is big O of log n times n squared. Okay, next one show that 1 plus 2 plus n is big theta n squared. So to prove big theta, we need to prove big O and big omega. Okay, so we need to show that 1 plus 2 plus n is big O of n squared, and it is also big omega of n squared. Okay, so next step, you need to try to find the witness C and K. In one case, uh, 1 plus 2 plus n is less than n squared. Okay, so first one is easy. If you replace 1, 2, 3, 4 by n, n, then you can have this inequality. Okay, this helps us to prove that 1 plus 2 plus n is equal of n squared. If we have this term is less than equal to n squared, then we can take the witness equals 1 and k equals 1. Okay, I hope you can check our course slides to see how we prove that 1 plus 2 plus n is big omega n squared. Okay, the last one should be fine because we need to calculate the worst case complexity of bubble sort. Okay, once you try to calculate how many times we use comparison, then we can get this number n squared. All right. Any question for the midterm examination? Oh, okay. If you have any questions, for example, calculation of your score is wrong, or you think your answer is correct, or you think the teammate is making course for you, then you can write your explanations in the right hand side of the speaker paper. Then we will collect all your paper back to see if there's any chance we can give you more points. Okay, so try to write your explanations to earn more points. If you think there is something wrong of your explanation, or you need to explain something to clarify the misunderstanding, then maybe we can give you more points. So please write down your explanations on the first page of the top and right corners. Okay, today I would like to introduce the chapter 5, which is induction and recursion. So in this chapter, you will see mathematical induction and particularly strong induction, well ordering, and the definition of recursion, and then how we apply mathematical induction to
a recursive defined set. So we call this structural induction. So let's see the basic form of mathematical induction in section 5.1. Okay, so we will see what is mathematical induction and some examples, and how we make mistakes when we prove by mathematical induction, and some guidelines when you write mathematical induction next time. Okay, maybe we can start from a very simple example of writing an infinity letters. Okay, so assume we have infinite letters and we have two rules to climb this ladder. We can reach the first rung of the ladder. Okay, because we have infinite run of this ladder. Run 1, 2, run 3, and so on. And then the second rule, if we can reach a particular rung of the ladder, then we can reach the next rung. Okay, so by these two rules, can we prove that we can reach each rung or every rung of this ladder? Okay, let's see how we apply these two rules. Because the rule 1 tells us we can reach the first rung of the ladder. So now we can standing from the ground and step to rung 1. Okay, and then by rule 2, if we can reach a particular rung of the ladder, then we can reach the next rung. So now we are standing on the first rung of the ladder. By rule 2, we can step to the second rung. Next, we can apply rule 2 again and again. If we are on step 2, then we are on second rung, then we can move to rung 3 and rung 4 by using the rule 2. Okay, so this tells us maybe we can use this concept to prove for all n from 1, 2, 3, 4 to infinity. If Pn is true, then we can infer to Pn plus 1. All right, so the principle of mathematical induction tells us if we want to prove P of n is true for all positive integer n, then we need to complete two steps. The first step is basis step. We need to show that P1 is true. And then for second step, the active step, we need to show that if P is true, then P of K1 is also true. So it sounds like very similar to our previous ladder example. Because P of n is true for all possible integer n, then we start from P of 1. Firstly, we prove that P of 1 is true. Then we can try the second principle. Okay. If P of k is true, then P of k plus 1 is true. If we can reach the run k, then we can reach the next run, k plus 1. Okay, so we call this inductive hypothesis because usually for the inductive step, we assume P of k is true. We need to assume P of k is true. Then we try to prove P of k plus 1 is true. Okay, so what happens if we don't assume inductive hypothesis? Because we want to prove if P of k is true, then P of k plus 1 is true. And we need to assume inductive hypothesis. That is P of k is true. What happens if we don't assume P of k is true? What's the name of this proof? If P of k is false, because we already know if P and Q, if P is false, then Q, then if P and Q is definitely true. Okay, so it's meaningless, we need to prove this. What's the name of the proof? If P of k is false, then we try to prove P of k and P of k plus 1. Okay, very good. One extra point. Vacuous proof. Okay. If P then Q, we have P
k already false, then you can say it's Bangor's proof, and you don't write anything. Don't have to write anything because this is true by Bangor's proof. So we are trying to avoid Bangor's proof. So we need to assume P of k is true. This is what is called inductive hypothesis. Once we assume P of k is true, then we need to prove that if this is true, P of k plus 1 is also true. Okay, so next, let's see. For mathematical induction, actually we can write into the form we have learned in chapter 1, because if P of y is true, and for all k, if P of k is true, then P of k plus 1 is also true. We have both terms is true. Then we can infer for all n, P of a is true. So this is what is mathematical induction. Okay, let's see. In the proof of mathematical induction, we don't assume P of A is true for all positive integers. Instead, we only assume if P of K is true, then P of K plus 1 must be true. Okay, so this is something you can notice for inductive step. Then for basic step, you can notice that we don't always assume the starting point is 1. Because in the previous example, we tried to prove that P of 1 is true. But in the next few examples, you can see the starting point can be other integers b. Okay, if P of b is true, then we try to prove b plus 1, b plus 2 is also true. Okay, so we have different starting points. Okay, next, let's see how we write the formal steps of mathematical induction to show that 1 plus 2 plus n equals n times n plus 1 divided by 2. Okay, let's see. For the basic step, we need to prove that P of 1 is true. Okay, so let's find the left hand side and right hand side. What happens when n is 1? Okay, so in the left hand side, n is 1, then we have only 1 here. For the right hand side, we have 1 times 1 plus 1 divided by 2. So the result is also 1. Okay, so we have 1 in the left hand side and 1 in the right hand side. So we know P of 1 is true. This is for basic step. Let's see for inductive step. We need to write inductive hypothesis first. So we assume for P of k is true. Then what is inductive hypothesis? So if we replace n by k in the question, then we have 1 plus 2 plus 3 plus something 2 plus k, which equals k times k plus 1 divided by 2. This is a complete inductive hypothesis. So we need to write this first. Okay, and then we try to prove that P of k plus 1 is true. Okay, so let's see how we prove we have this equality is true. Because when we have 1 plus 2 plus k plus k plus 1, then we need to apply the results from inductive hypothesis. Because we already have 1 plus 2 plus k, which equals k times k plus 1 divided by 2. And we have one additional term here, k plus 1. Let's see how we combine those terms. We have a common term k plus 1 here. So we can write 2 times k plus 1 plus k times k plus 1 divided by 2. And we have a common factors k plus 1. So we have k plus 1 times k plus 2 divided by 2. So this tells us, actually, if we plus 1, 2 to k plus 1, then the result equals k plus 1 times k plus 2 divided by 2.
Okay, let's see next example. You will see more exercise in your homework assignment to ask you to conjecture and prove the formula by mathematical induction. So let's see this example. Can you conjecture and prove a correct formula for the sum of the first n positive odd integers? Sum of first n positive integers. Okay, so let's see. If we have first one positive odd integer, that will be 1. So if we have first two positive odd integers, it will be 1 plus by 3. The result is 4. If we have three positive odd integers, 1 plus 3 plus 5, the result is 9. Okay. If you see more examples, you can see 1 3 plus 1 plus 3 plus 5 plus 7, the result is 16. Okay, now we have 4, 9, 16, and 25. So now we can conjecture a formula. Actually, if we add first n positive odd integers, 1, 3, 5, 2, 2, n minus 1, the result equals n squared. Okay, so this is the formula we conjectured. So now we need to prove by mathematical induction to show that this formula is correct. So let's see how we write the basic step. For p of 1, in the left-hand side we have 1. In the right-hand side, 1 squared is also 1. So basic step. Okay. Let's see inductive step. Okay, we assume P of k is true, and then P of k plus 1 is also true. So we assume the inductive hypothesis. Okay, if 1 plus 3 plus 5 to P of k, so we have 2k minus 1, which equals k squared. Okay, next, we add additional term, which is the next positive odd integers. Okay, so we have 1 plus 3 plus 5 plus 2k minus 1. So the next positive integer is plus 1. Now we apply the inductive hypothesis because first k positive odd integers, the sufficient equals k squared. Now we have k squared plus 2k plus 1. So now you can see k plus 1 squared. Okay, so the second step, the inductive step, we prove that P of k plus 1 is true. So we have proved that the sum of first n positive integers, the result is n squared. Okay, you may also see some questions to ask you to prove inequalities. For example, we need to prove n is less than 2 to the power of n for all positive integer n. Okay, we know this fact already, right? Because this is linear function or polynomial function. And this is exponential function. We already know that exponential function grows faster than polynomial function. So for all positive integer n, actually the polynomial function n is less than the exponential function 2 to the power of n. Now we have a full proof by mathematical induction. So let's see, for basic step, if p of 1, let's see, in the left hand side we have 1, in the right hand side we have 2 to the power of 1. So 1 is less than 2. So p of 1, we prove that p is true. Next, let's see inductive step. We assume p of k is true. So this means k is less than 2 to the power of k.
this inductive hypothesis, we try to prove P of k plus 1 is also true. So let's see. So for P of k plus 1, we have k plus 1. And then we can use the inductive hypothesis because we already know k is less than 2 to the power of k. So we can write this inequality k plus 1 less than 2 to the power of k plus 1. We just replace k less than 2 to the power of k in this inequality. Okay. And then let's see what is the goal. The goal is k plus 1 is less than 2 to the power of k plus 1. So this is our final goal, 2 to the power of k plus 1. So we can rewrite this a little bit because 2 to the power of k plus 1 actually is 2 to the power of k times 2. Okay, so we just separate it into two terms. Okay, then we can see how we connect the previous terms 2 to the power of k plus 1 to 2 times 2k. Okay, so we already know that if we have 2 times 2 to the power of k, that means we have two terms. The term is 2 to the power of k. So we can write 2 to the power of k plus 2 to the power of k. And then we compare to the previous terms. Actually, this inequality holds because now we have 1 here and we have 2 to the power of k here. So for k of any positive integers, this inequality holds. Okay, now we connect our previous terms to our goal 2 to the power of k plus 1. So if we can complete the inductive step, then actually we complete this function. N is less than 2 to the power of n, which is holds for all positive integers n.
All right, next let's see more example of mathematical induction. If we want to prove 2 to the power of n is less than factorial of n, okay, for every integer n is larger than or equal to 4. Okay, so we know this is true because the exponential function grows slower than factorial function. So this is the thing which grows the fastest. Okay, so let's see how we prove by mathematical induction for every integer n is larger or equal to 4. Alright, so let's see our basic step. Our starting point is not from n equals 1 because it tells us for every integer n larger or equal to 4. So we try p of 4 first. Okay, let's see the left hand side. If n equals 4, then we have 2 to the power of 4. And we need to extend it if it is less than the factorial of 4. So factorial of 4 actually is 4 times 3 times 2 times 1. Okay, so it will be 24. And 2 to the power of 4, which is 16. So the inequality holds. Let's move to the inductive step. Once we have P of k, which is true, so we can write this inductive hypothesis first. 2 to the power of k, which is less than the factorial of k. Then let's see how we prove that P of k plus 1 is true. Okay, so let's see. We have P of k plus 1, then in the left hand side, we have 2 to the power of k plus 1. Okay. Now you need to think of some ways to apply inductive hypothesis. Because our inductive hypothesis is 2 to the power of k less than factorial k. So we can separate the power by 2 times 2 to the power of k. Okay, once we have 2 times this term, actually this is p of k. So we can write it's less than 2
times factorial of k. Okay, if you write to this step and you stop, maybe you can think of what is the goal, because we need to get the results 2/12 of k plus 1, which is less than k plus 1, the factorial of k plus 1. Okay, then what is factorial k plus 1? Actually, it's factorial k times k plus 1. So we can see when we have 2 times factorial of k, does this smaller or less than k plus 1 times factorial k? This is true because our starting point k is larger than 4. Okay, so k plus 1 is larger or equal to 5, so which is larger than 2. Okay, now we have the connection from the previous step, and when we trace back from our goal, we know this step actually is true. Okay, so now we complete the proof of 2 to the power of n is this factorial of n for every positive integer when n is larger or equal to 4. All right, let's see next example. Use mathematical induction to prove that n cubic minus n is divisible by 3 for every positive integer n. Okay, so it's not very intuitive, right? Why n cubic minus n is divisible by 3? All right, so if it's not that intuitive, maybe we can try basic step first. Okay, what is P of 1? P of 1 is 1 cubic minus 1, which is 0. Okay, so 0 can be divisible by 3. That's okay. Next, let's see inductive step. If we assume P of k is true, that means k cubic minus k is divisible by 3. Okay, so next, let's see how we prove P of k plus 1. Okay, so let's see what is P of k plus 1. Actually, it's k plus 1 cubic minus k plus 1. So we need to prove this one is divisible by 3 using inductive hypothesis. So our inductive hypothesis is this term. So we need to have this term first. So let's see how we rewrite this term to have something of this one. So maybe we can expand this term. K plus 1 cubic actually is k cubic plus 3k squared plus 3k plus 1 and minus k plus 1. So we need to do something to have k cubic minus k. Actually, we have that term because we have k cubic here, and we have minus k here. So we can put them together to have p cubic minus k, and then combine the resting term. So the resting term is 3k squared plus 3k plus 1 and minus 1. So these two terms is here. So we have only 3k squared plus 3k. Then we get common factor 3. So we have k squared plus k. Okay, now we know that from inductive hypothesis, k cubic minus k, this term is divisible by 3. And we have the second term, which is 3 times something. Okay, so we know this term is also divisible by 3. Okay, so now we can see actually p of k is also divisible by 3. All right, next let's see some example of the set. Okay, we can also prove some properties of the set using mathematical induction. Because for set we have distinct elements 1, 2, 3, 4, 5. Okay, so it's also follow the mathematical induction. We have some property p of n. All right, let's see this example. Use mathematical induction to show that if S is finite set with n element, where n is a non-negative integers, then S has 2 to the power of n subset. Okay, we know this fact already in chapter 2, right? For every set which has n elements, the subset is 2 to the power of n. How we know that? Why the number of subsets with n elements in the set is 2 to the power of n? Yeah, that's right. Because we can choose each element, choose or not choose into the subset. So for the first element, we have two choices. For the second element, we also have two choices. If we have n elements, then it will be 2 times 2 times 2 times 2, n times. So this is a subset. Once we know that, then this question is very simple. Let's see how we prove by mathematical induction. Okay, if P of n is our proposition, a set with n elements has two power of n subset, then let's see P of 0. Okay, if we have 0 elements, then 2 to the power of 0 is 1. So what is the subset of an empty set? Just empty set, right? Itself. Okay. So we know empty set is a subset of any set, and S is a subset of S itself. So if we have only one empty set, then we have empty set as a subset. Okay, so this is that. Next, let's see inductive step. Assume we have P of k is true for arbitrary non-negative integer k, then let's see our inductive hypothesis, how to expand to k plus 1. And once we have k plus 1 elements, then we can separate that element A. Okay, so for example, now we have k plus 1 elements, we call this set T. Okay, now we can separate this one additional element by S union this element A to give a complete set of T. Okay, now we know the causality of T is S plus 1. So the causality of S actually is K, right? Okay. This is how we can apply inductive hypothesis. Okay. Because if S, the causality has K elements, then the number of subset is 2 to the power of K, then we can choose this element or not choose elements. Okay. So this gives us two different choices. And from the set S, we have 2 to the power of K subset. Therefore, we have two different choices for the element A. Then for the set T, totally we have 2 times 2 to the power of K subset. Okay, so that will be 2 to the power of k plus 1. Alright, so I believe if you have the core concept how to apply inductive hypothesis, then we can solve every difficult puzzles of questions and use mathematical induction to prove that question. Okay, next let's see this problem telling the checkerboards. Okay, show that for every 2 to the power of n times 2 to the power of n checkerboard with one square removed can be solved using the wide triangles. Okay, so this is L-shaped triangles. So it's like dominoes, but we have a special shape for these dominoes. We call this triangles. checkerboard. The size is 2 to the power of n times 2 to the power of n. Okay, maybe we can see the example of basis that when n is 1. Okay, let's see. When p of 1, that means the checkerboard is 2 times 2. Okay, so this is the size of 2 times 2 of the checkerboard. Okay, and then we can tile with right triangles with one square removed. Okay, so if we remove this square, then the rest of one can be tiled using these U-shaped triangles. We have 4 different cases. You can remove this square, remove this square, this one, or that one. For each case, we can use an U-shaped triangles to tile this checkerboard. Okay, so P of 1 is okay. Let's see what happened when we have 2 to the power of k times 2 to the power of k checkerboard. Okay, so now the checkerboard becomes so large. Okay. How we do that? We can be found by U-shaped triangles with one square removed. Okay, so now we have the inductive hypothesis. We assume that if the size is 2 to the power of k times 2 to the power of k, it can be tiled with these U-shaped triangles with one square removed. So this is our inductive hypothesis. Let's see how we prove that p of k plus 1 is also true. Okay. When n equals k plus 1, that means the size is doubled by inductive hypothesis. So we have a larger checkerboard 2 to the power of k plus 1 times 2 to the power of k plus 1 with one square. Okay, so remember, we need to apply inductive hypothesis because we already assumed this is true. So now we can partition this checkerboard by 4 different parts. Okay. Once we partition by 4 different parts, that means for each part, the size of this square is 2 to the power k times 2 to the power k. So that means this part can be tiled by the L-shaped triangles with one square removed. Okay. For example, we remove this square. And then for the second part, we remove this square. And for this part, we remove this square. And for this part, we can remove any square within this part. So now we can see if we remove this square, this one, and this one, actually we can use another L-shaped triangles for this region. And then we just remove one square for this 2 to the power of k plus 1 square. Alright, so now you can see, actually this part can be tiled by L-shaped triangles and these three parts well. And then we can also fill one L-shaped triangles here. So that makes the range of 2 to the power of k plus 1 times 2 to the power of k plus 1 with L-shaped triangles by one square removed. Okay, so this is how we calculate a p of k plus 1.好，这一题大家 OK 吗？听不懂是不是？好，那我们用中文再讲一次好了哈。就是呢，我们有一个假设是2倍数乘2倍数的2乘2的棋盘格，好，那这个棋盘格呢，可以用一个积木，这个积木是 L 形状的积木去填满，好，那我们要证明这个2倍数的棋盘格，不论它是2 to the power of n， 2的 n 次方 n 是多少，它都可以用这个 L 形状的积木去填满。好，那我们要证明这件事情，当然就从 P of 1开始。那当这个棋盘格是2乘2这个大小的时候，那我们就可以它是可以用 L 形状填满的。那我们的前提呢是可以从这 这个棋盘格去掉一个方块的正方形，去掉了这一个方块之后呢，它就可以用模型状的积木填满。好，那我们如果是2×2，你去掉其中一个方块，那剩下这个地方就可以用一个流形状的积木把它塞进去，就填满了。好，所以 P of Y 是可以的吗？好，那我们接下来就看看，假设这个棋盘格变得很大的时候该怎么办呢？好，那我们当然还是假设我们的 inductive hypothesis， 当这个棋盘格是2的 k 次方的时候，即使它这么大，我们都假设去掉一个方块之后，它是可以被 L 形状的积木填满的。好，那这个是我们的 inductive hypothesis。好，那假设这个情形是成立的，那我们接下来就看看，当这个棋盘格长大到2的 k 加1次方的时候，好，它要怎么被 L 形状的积木填满？那当然我们前面已经说过，这个你要证明 P of k 加1，你一定要用到这个我们的 inductive hypothesis， 就是 P of k。如果 P of k 是成立的，我们再来推 P of k 加1。所以我们怎么用 P of k 的结论呢？就是 inductive hypothesis。当然就是我们把这个棋盘格它的尺寸是2的 k 加1次方，我们把它切成4格，切成4格之后，每一格是不是就是2的 k 次方的大小？因为实际上这边就会是2的 k 乘上2，2的 k 次方乘上2，所以总共就是有4块2的 k 次方。好，那每一个都是2的 k 次方之后，我们的 inductive hypothesis 告诉我们，其实2的 k 次方只要移掉一个方块就能够被流形状的积木填满。那这一块我们是不是可以移掉这一个方块？移掉这个方块之后，这一块就可以被流形状的填满。这个是我们的 inductive hypothesis。那同样的，这一块也是2的 k 次方，我只要移掉这一个方块，这一块是不是也可以被流形积木填满？那这一块是一样，最后一块我们就随便移啊，你可以移掉任意一个方块。那移掉这样子的情形之后呢，现在这整个东西啊，我们就用多的一个流形状的方块把这个地方填满。这个地方也是一个流形的积木可以填满的范围。那我们移掉这一块之后，是不是这整块都可以用流形的积木填满？白色这一块可以，白色这一块可以，白色这一块可以，蓝色这一块可以。去掉这一块之后，这一块不可以。那是不是整块就可以用流形的积木填满？好。All right, maybe we can stop here and let's discuss this in Thursday.
期中考考卷交回来。
所有同学都要交哦。
所有人都交回来了。然后那个解答跟评分标准都上传到 YouTube 上面，回去可以看。
就是对于当时的它是那但是我们现在要证明的是 P of k 加1要成立。那 P of k 加1就是它的元素多的原因，它来从 k 的元素变成 k 加1的元素。那所以变成 k 加1的元素之后呢，我们就可以把它，因为要把 k 的元素的2k 这个东西要拿进来用，所以我们就把新的这个积分分成是 s 的，然后再加上 s 是剩下所有的，对对对。假设我们这个有 k 加1个，我就把那一个分出来，剩下所有的叫做 s。所以就好，那你就把你的语录写下来，觉得你没有错，请就要再说一下。好，对，丢到那个日记里面。
之后会再发回来。
我们好像要做那个课程认证，所以可能好像
成绩到时候再公布，应该可以再公布，但就考卷可能就不会发了。
可是那这样我怎么知道我的有没有被记到？
分数会再公布，分数会更新这样。
之后就不能再 argue 这样。
就不能让。对，
哦，
你写完之后，
我不能说现在那种
这因为我们老师跟助教会再重新看，看你讲的有没有道理，这样就是这个没有需要 argue。看完之后就知道你讲的有没有道理。
我上面E-code上面有发一份，对，有评分标。
这有没有高考这因为这个的成绩
我没有打错。
没有我知道，就是因为我自己没有挂号，然后你帮我画起来。
你说哪一个？
因为 N 的成绩比截图还要高，所以我觉得不挂号它也会显示，然后它再过来。
我想一下，反正这到时候你有调回去了吗？
这功课那时候没有被我们
没有被算错吗？
对啊。
那就是功课我改错。
可是功课解答是。
功课解答跟这个一样吗？就跟这个上面写的。
我叫来要救了。改错其实我写哪一个错就。我写先改。我去看。我写这个。他扣的那个
新的就不一样。
对。我没有放上去。